In this lecture and the following couple of lectures, I am going to talk about properties of MSK waveform. The first property that I like to talk about is the fact that the MSK waveform has a constant envelope. Constant envelope. Although the individual I and Q channels seem to be amplitude modulated DSBSC kind of waveforms, the final overall MSK modulated waveform is a constant amplitude or a constant envelope signal. If you look at the waveforms here, this is the I channel. This is the I channel. This we have already seen this, and this is a Q channel. And the I channel is modulated by cosine waveform and the Q channel is modulated by sine waveform, and these waveforms look like a amplitude modulated signal, that is DSB SC kind of modulated waveform. Okay, but if you look at the final MSK modulated waveform, this is MSK modulated waveform, the amplitude is constant. Okay, constant amplitude or constant envelope. The envelope is constant, or I can say amplitude is constant. Okay, now let us prove this mathematically, how we can say the amplitude is constant. Okay, but all you have to do is look at the complex envelope. So this is a complex envelope. The dotted line is complex envelope. Okay, dotted lines. These are complex envelope, and this is the Q channel complex envelope, and this dotted line is the I channel complex envelope. And we know that the incoming bit stream is divided into two bit streams. One is even bit stream. This we already know. One is odd bit streams, and the even bit streams we call as I channel, and this is we call Q channel. And this is even bit. How do you represent even bit? S of t minus let's say 2 times LTB, because the duration is 2 times TB, that's why. Or you can say S of t minus capital T. Okay, T minus L times capital T. Let me write properly. T minus L capital T. And for odd bits, how do you write? S of t minus LT minus T by 2, or S of t minus 2 times LTB minus TB. This is a notation of the pulse, representation of the pulses. And in the MSK waveform, we used half cosine pulses. For I channel, we used half cosine pulse, that is half cos of pi t by capital T. For Q channels, we use half set of this Q cos pi t by t, offset of cos of capital pi t by t. That means t by 2 delayed. Therefore, the Q channel uses t by 2 delayed version of cos of pi t by capital T. So delayed version means your S of t minus LT minus T by 2, which is cos of pi. Let me write properly. Cos of pi times t minus capital T by 2 folded by capital T. If you simplify this, you will get cos of pi t by capital T minus pi by 2, and this is sin pi t by 2. So half sine pulse we will use for Q channels, and half cosine pulse that we will use for I channels. Therefore, we know how to represent mathematically the complex baseband representation of this modulated waveform. In the previous lecture we have wrote down this summation of a to l complex I know even amplitudes times s of t minus lt, okay, and where l ranges from minus infinity to plus infinity, plus j times sigma l is equal to minus infinity to plus infinity a to l plus 1 s of t minus lt minus t by 2. And now this will be replaced by cos of pi t by 2, cos of pi t by capital T, and this will be replaced by sin of pi t by capital T. And this is the amplitude of the even pulse, amplitude of even bit pulse, even bit streams, and this is the amplitude of odd bit streams, amplitude of odd bit streams. Therefore we defined either the amplitude is plus a or minus a. Therefore a to l is equal to, or al, let me in general al equal to plus a if lth bit is 1, if lth bit is 1, and minus a if lth bit is 0. Therefore this is our setup. Now we need to prove that. What is our proof? No, what do we need to prove? It should have the okay, it must have the constant envelope. Okay, so the proof is like really a one line proof. By observations, you can prove this. Okay, so look at here, this I channel and Q channel has basically two pulse shapes. One is cosine, half cosine pulse shape, and it is t by 2 shifted version, which is the sine pulse shape. Okay, substitute that and you can easily prove. So the proof is like C of t is equal to summation of which is, it takes either plus a or minus a times cos of pi t by capital T plus j times summation of plus or minus a times sine of pi t by 2. Now I want to say the envelope or amplitude of the C of t should be equal to 1, where L equal to minus infinity to plus infinity. And now for all L it takes either plus a or minus a, so I can remove this summation. So plus or minus a times cos of pi t by t plus j times, I'm sorry, plus let me put a plus or minus a times sine of pi t by t. So let us assume a is equal to 1. Let some value later. Let a is equal to 1. Then what happens? This is equal to plus or minus cos of pi t by capital T plus or minus j times sine of pi t by capital T. Right, now this is your C of t. It is quite obvious that no matter what the signs, okay, might be, as far as the magnitude of the C of t is concerned, it is obviously going to be equal to 1. So if you take magnitude of this, then it is equal to square root of cos square pi t by t can plus like cos square pi t by capital T plus sin square pi t by capital T, which is equal to 1. Therefore the magnitude is always equal to 1. So that shows that there is no amplitude fluctuations. So this result shows that no amplitude fluctuation in an MSK waveform. Okay, so now that is a very desirable property. This is very desirable property. Okay, desirable property in any digital modulation waveform. Okay, so because the MSK will be relatively insensitive to non-linearities. Whenever you have constant amplitude, then it is insensitive to non-linearities, which may be present in your system, and that is a major reason for the popularity of MSK waveform in such applications. Okay, because of this constant envelope, this MSK is very popularly used in digital communication. Okay, so especially let's say if you take a satellite channels where non-linearities are a fairly important class of problems to worry about. So in such a type of applications, this MSK is a saver. So it will overcome all the difficulties, and it performs very well. So that is why the MSK is very popular in digital communication systems. Okay, so let me stop at this point, and the next property I'll talk in the following lecture. Thank you.